So, now we will study the gamma distribution, which is the second distribution in the class of absolutely continuous distributions which we are studying here. So, first let me define what is a gamma function. A gamma function is a real valued function, in fact a positive real valued function defined on 0 to infinity, and this is given by gamma alpha as 0 to infinity e to power minus t to power alpha minus 1 dt. Now, one can show that for alpha greater than 0, this integral is always finite. So, that means gamma function is well defined for any alpha greater than 0. So, few properties of a gamma function, one can see that gamma alpha plus 1 is same as alpha gamma alpha, which is straightforward if you do integration by parts, taking this as an integrating e to power minus t as an integrating factor and t to power alpha as the differentiating factor. So, once you do that, gamma alpha plus 1 turns out to be alpha gamma alpha. So, if alpha is an integer, then I know that gamma alpha is same as alpha minus 1 gamma alpha minus 1. Alpha minus 1 is same as alpha minus 2 gamma alpha minus 2. So, this will go alpha minus 1 alpha minus 2, finally 1 times gamma 1, and you can see gamma 1 is nothing but 0 to infinity e to power minus t dt, which is nothing but 1. So, this whole thing becomes factorial alpha minus 1. So, if alpha is an integer, positive integer, then gamma alpha is factorial alpha minus 1. Now, one can see gamma half is same as 0 to infinity e to power minus t by root t dt. This is if one has to do this, what one does is this integral 0 to infinity e to power minus t by root t dt. Let me put t is equal to x square. So, let me put t is equal to x square, then that means t is x square. So, then what you get is dt as 2x dx. So, e to power minus t to power half minus 1. So, t is same as x square. So, this can be converted into integral of the type 0 to infinity e to power minus x square constant times e to power minus x square dx, because then e to power minus t you put as x square. So, this becomes dt becomes twice x dx. So, gamma half that means this integral becomes 0 to infinity e to power minus x square, dt becomes 2x dx, and root t becomes again x. So, this gets cancelled. So, 2 times dx, and then one can get the value of I is equal to 0 to infinity e to power minus x square dx through the following. If one look at I square, this same as 0 to infinity e to power minus x square dx multiplied by 0 to infinity multiplied by 0 to infinity e to power minus y square dy. So, if one takes it over here, so I square turns out to be 0 to infinity e to power minus x square plus y square dx dy. Now, one can put the polar coordinate transformation, x is equal to r cos theta, y is equal to r sin theta. Jacobian will turn out to be r would be greater than 0, theta between 0 to 2 pi, and one can get gamma half then as root pi. So, one can try this. This is a simple exercise. This was done in one of the assignments. So, let us move further. So, what we observe is 0 to infinity e to power minus t to power alpha minus 1 dt by gamma alpha is 1. So, even if I replace t, let us say x by theta, then what turns out to be 1 upon theta to power alpha gamma alpha 0 to infinity e to power minus x by theta x to power alpha minus 1 dx turns out to be 1. And here fx is also non-negative. So, that means one can take this to be a PDF. This is if x greater than 0, 0 otherwise. Such a random variable is said to have a gamma distribution with shape parameter alpha and scale parameter theta greater than 0. Now, alpha determines the shape. As you can see, if alpha is less than 1, this implies that fx is always decreasing. So, for alpha less than or equal to 1, fx is always decreasing. If alpha is greater than 1, then fx would, one can easily see, would look like at x equal to 0, this would be 0. So, it would be unimodal kind of a distribution. So, it would be slightly skewed, but it would be looking like this for alpha greater than 1. So, that is how the PDF of gamma looks like. So, one can look at clearly fxx is greater than or equal to 0, minus infinity to infinity fxx dx is 1 by theta power alpha gamma alpha, 0 to infinity e power minus x by theta x power alpha minus 1 dx, which is same as 1 upon gamma alpha because I put x by theta as t. So, dx by theta becomes dt, and then you simplify, it turns out to be 1 upon gamma alpha e to power minus t to power alpha minus 1 dt, which turns out to be 1. So, it is a proper PDF. So, let us try to see the movement generating function. mxt is expected value of e to power minus tx, which is e to power tx fxx dx. fxx is positive only in 0 to infinity, 0 to infinity, e to power tx, fxx is e to power minus x by theta, x to power alpha minus 1, divided by theta power alpha gamma alpha. So, I combine this 1 upon theta power alpha gamma alpha, 0 to infinity, this becomes e to power minus 1 minus t by theta. So, I combine these two terms, x to power alpha minus 1. But this integral is finite only when this quantity is positive. Otherwise, this will, because then it will become e to power some positive power that finally at infinity it would explode. So, I need 1 minus t theta by theta to be greater than 0 for this integral to be convergent, which is equivalent to saying that t is less than 1 by theta. That is what I have. And in that case, I know this integral because I know that 0 to infinity e to power minus x by theta x to power alpha minus 1 dx is same as theta to power alpha into gamma alpha. So, this would be 1 minus t theta by theta to power minus alpha gamma alpha, and theta power alpha gamma alpha was already there. So, this turns out to be 1 minus t theta to power minus alpha for t less than 1 by theta. Now, theta is positive, so 0 is over here. So, for 1 t less than over here, the movement generating function is finite. So, that means movement generating function is finite in a neighborhood of 0. So, I can say that all movements are finite, and one can get movements either by expanding mxt or by differentiating mxt. So, let us try to see that. I try to consider the expansion of this binomial expansion with negative power. So, mxt is turns out to be 1 plus alpha t theta plus alpha into alpha plus 1 by factorial 2 t theta whole square plus alpha into alpha plus 1 alpha plus 2 by factorial 3 t theta cube for t less than 1 by theta. So, let us try to see mean, which is mu, which is expected value of x, which is coefficient of t in mxt. Coefficient of t in mxt is alpha theta. Expected value of x square, which is coefficient of t square by factorial t in mxt, which is over here, which is alpha into alpha plus 1 theta square. Then variance is nothing but expected value of x square minus value of x whole square, which is same as this minus alpha square theta square. This turns out to be alpha theta square. So, mean is alpha theta and variance is alpha theta square. A gamma 1 theta distribution, so that means when shape parameter is 1, then gamma distribution is called the exponential distribution. So, a gamma 1 theta distribution is called exponential distribution. Then I know that for gamma the mean is alpha theta. So, in this case, since alpha is 1, the mean would be theta. So, that is why this parameter is nothing but the mean. And we write down this as if x1 has exponential theta, then its PDF is given by this. So, one can see in this case the PDF is a decreasing function. As x goes to infinity, it goes to 0. So, the PDF would look like this. Now, this exponential distribution has a very distinct property which we will discuss a little bit later. But let us see what is a mean. Mu. Mu is alpha theta for gamma. For exponential alpha is 1, so mean is theta. Variance is alpha theta square for gamma. Here alpha is 1, so variance will become theta square. mx1t is 1 minus t theta to power minus alpha. Alpha is 1, so 1 minus t theta to power minus 1 for t less than 1 by theta. So, these are the properties of exponential distribution. Now, if your shape parameter is n by 2 and the scale parameter is 2, then such a distribution is called the chi-square distribution with n degrees of freedom. Now, here n is a positive integer, and we denote a chi-square distribution with n degrees of freedom by chi-square n. So, clearly, if x2 has chi-square distribution with n degrees of freedom, its PDF would be 1 by 2 to power n by 2, gamma n by 2, e to the power minus x by 2, x to the power n by 2 minus 1, if x greater than 0, 0 otherwise. So, mean is nothing but alpha theta, alpha is n by 2, theta is 2, so mean is nothing but n. So, mean of chi-square distribution is nothing but same as its degrees of freedom, which is n. Variance is same as alpha theta square, alpha is n by 2, theta square is 4, so it becomes 2n. Its MGF is nothing but 1 minus theta t, theta is 2, so 1 minus 2t to the power minus alpha, which is n by 2 for t less than n by 2. Now, this chi-square distribution turns out to be very useful in various statistical inference problems. So, for that reason, quantiles of gamma distributions are tabulated in various textbooks, especially the chi-square quantiles can be found in almost every book on statistics, elementary book on statistics. So, this is about chi-square. So, chi-square also, because n is an integer, so one can look at if n is greater than or equal to 2, for n is equal to 2, it would be an exponential distribution. Otherwise, its PDF would be again like this for n greater than or equal to 3. Let us try to see the reproductive property of a gamma distribution. So, let x1, x2, xk be independent random variables with xi having gamma alpha I theta distribution, where the shape parameter alpha is positive, theta is positive. Then their sum again has gamma distribution with shape parameter getting added and scale parameter remaining the same, because I have assumed that all of them have the same scale parameter theta. So, if your gamma distributions are such that they have different shape parameters, but the scale parameter is the same and they are independent, then their sum is again gamma with degrees of, with shape parameter getting added and scale parameter remaining as it is. So, let us try to see m by t, which is equal to t to the power y, and I know that movement generating function of sum of independent random variables is same as the product of marginals. So, it is product I is equal to 1 to k m xi t, which is product I is equal to 1 to k, xi is gamma alpha I theta. So, I know its movement generating function is nothing but 1 minus theta t to the power minus alpha I. Theta is same in each of them. Note that if theta I was different, then it would not have been possible to write down it in 1 minus theta t to the power minus summation I is equal to 1 to k alpha I. So, it is important that all theta i's are same. If that is happening, then I can write down this product as 1 minus theta t to the power minus summation I is equal to 1 to k alpha I for t less than 1 by theta. This is clearly MGF of gamma with scale with shape parameter as summation I is equal to 1 to k alpha I, scale parameter as theta. So, hence the result follows. So, gamma distribution has reproductive property. So, in particular, exponential distribution and chi-square distribution have reproductive property. So, which is what it says, that x1, x2, xk be independent random variables, and suppose y is same as sum of xi's. If xi is exponential, then y, because exponential, that means alpha I, each alpha I is 1, then y would have gamma with summation alpha I would be equal to 1, 1, 1 added k times, so k theta. If xi is chi-square on ni, which is gamma theta is equal to 2, alpha is n by 2. So, that means alpha gets added, so that becomes summation ni by 2. So, degrees of freedom is nothing but summation I is equal to 1 to k summation ni. So, suppose that let us try to see an interpretation of exponential distribution. So, suppose x has exponential theta, where theta is positive. Then let us see what is the probability x greater than s. Probability x greater than s is s to infinity 1 by theta e to the power minus x by theta. So, since s is positive, if you integrate it, you get e to the power minus s by theta. So, for exponential distribution, probability that x is greater than s is e to the power minus s by theta. Let us consider for s positive and t positive, what is the probability that x is greater than s plus t divided by x greater than c. So, this would be probability that x greater than s plus t, x greater than s, divided by probability x greater than s. But s and t both are positive, so x greater than s plus t and x greater than s, their intersection would be x greater than s plus t divided by x greater than s. Now x greater than s plus t, you know, is nothing but e power minus s plus t by theta, divided by x greater than s is nothing but e power minus s by theta. So e power minus s by theta gets cancelled in numerator and denominator, so you get e power minus t by theta, which is same as probability x greater than t. So note that for exponential distribution, what we have is probability x greater than s plus t, given that x greater than s is same as probability x greater than t. We'll try to interpret this property. So what we have for exponential distribution is probability x greater than s plus t, given x greater than s is same as probability x greater than t, which is equivalent to saying that probability x greater than s plus t is same as probability x greater than s into probability x greater than t. Let us try to interpret this property. So suppose x, which is exponential theta, denotes the lifetime of a component. So there is a component which has a random lifetime x. What does this property says? Given that the component has survived s units of time, the probability that its lifetime is greater than s plus t, so that means it would survive t additional units of time. So this probability is same as saying that given that the component has survived s units of time, the probability that it would survive t additional units of time is same as if a fresh component survives t units of time. So in a sense, the information that it has survived up to s units of time, that means it has become older, has no bearing on its remaining lifetime. That would be the same as that of a fresh unit. And that is what is being said over here. Then the property 1 about the lifetime of the component has the following interesting interpretation. Given that the component has survived s units of time, the probability that it will survive additional t units is the same as the probability that a fresh unit of age 0 will survive t units of time. In other words, the component is not aging with time. That means age has no bearing on its remaining lifetime. Or in other words, the used component is the same as the new one. So component is not aging. Now this property of a continuous random variable is also known as the lack of memory or memoryless property. So what we can say is exponential distribution has memoryless property. And why it is called a memoryless property? Because at each state the component forgets its age and behaves like a fresh component. So it is in this sense it has memoryless property. In fact, it so turns out that among continuous distributions concentrated on 0 to infinity, exponential distribution is the only distribution which has memoryless property, which is given in the form of following result. So let y be a continuous random variable with fy0 is 0. Then y has the lack of memory property if and only if y is exponential theta for some theta greater than 0. We know that if y is exponential theta for some theta greater than 0, then y certainly has lack of memory property. Now, it is the converse which we have to prove. That means if a distribution has, if a random variable has lack of memory property, then it has to be exponential. So conversely, suppose that y has lack of memory property. Note that the assumption is that y is continuous and fy0 is 0. So that is a part of assumption. So it is, this result holds for all the distributions which are concentrated on 0 to infinity and which are continuous. So f bar yt, which is same as 1 minus fyt, which is same as probability y greater than t. Now I know that probability y greater than s plus t because it has a lack of memory property, so it has same as probability y greater than s into probability y greater than t. Or in other words, f bar y s plus t is same as f bar y s into f bar yt. Now you can use induction to conclude that f bar y of s1 plus s2 plus sm is same as f bar y s1 multiplied by f bar y sm. It follows from this property just using induction. Now what I do is I take each si to be 1 by n, then it becomes f bar y of m by n. Each si is 1 by n, so f bar y to power 1 by n. These are m in number, so f bar y 1 by n to power m. So this is what it happens. Now I take again m as same as n, and each si to be 1 by n. So in fact here you take m is equal to n. So f bar y turns out to be f bar y 1 by n to power n, because I have taken m is equal to n. So, this f bar y n I replace here by f bar y to power 1 by n. So, then it becomes f bar y to power m by n is same as f bar y 1 to power m by n. So, that is what we get. So, f bar y m by n is same as f bar y 1 whole power m by n. Now, let lambda is same as f bar y. So, certainly lambda is between 0 and 1. Now, what I will show is lambda is equal to 0 and lambda is equal to 1 is not possible. Suppose lambda is 0, that means f bar y is 1. Then I know that f bar y 1 is same as f bar y 1 by n to power n. So, that means f bar y n 1 by n is 0. If lambda is 0, then f bar y 1 by n has to be 0 for every n. So, that means limit n going to infinity, f bar y 1 by n has to be 0, which is equivalent to saying that f bar y 0 is 0 because f bar y is given to be continuous. But f bar y is same as 1 minus f5, which is same as fy0 is 1. But which is contradiction, why? Because we are given that fy0 is 0. So, you cannot have lambda to be 0. Now, let us look at lambda as, if lambda is 1, then I know that f bar yn is same as f bar y 1 whole power n. So, this is 1. So, that means I take n going to infinity. So, f bar y infinity is 1. That means fy infinity, which is 1 minus f bar y infinity, is 0. But f being a distribution function, fy infinity has to be 1. So, even this is not possible. So, that means my lambda has to be strictly between 0 and 1. So, thus lambda has to be strictly between 0 to 1. So, if lambda is strictly between 0 to 1, I can always write down lambda as e to power minus 1 by theta for some theta greater than 0. So, let lambda is same as e to power minus 1 by theta, theta greater than 0. Then we have seen that f bar y to power m by n is same as f bar y 1 to power m by n. This same. So, f bar y 1 we have taken as lambda, which we have taken e to power minus m by n. So, it becomes e to power minus m by n theta. But m by n is any rational number. So, that means f bar y r is same as f bar y 1 to power r, which is same as e to power minus r by theta for any positive rational number r. So, here Q denotes the set of all positive numbers. What I have to show is, I will show that f bar y x is same as e to power minus x by theta for any x. Now, let x be any greater than 0. But we know that rationals are present everywhere in the real line. So, if x is any real number, I can always find a sequence xn of rationals such that xn converges to x, because these rationals are present everywhere. So, then since fy is continuous, fyx is same as limit n going to infinity fy xn, which is same as limit n going to infinity. For rationals xn, fy xn I know is e to power minus xn by theta. So, this becomes e to power minus x by theta. So, f bar yx turns out to be e to power minus x by theta, or fyx is 1 minus e to power minus x by theta for x greater than 0, and certainly this would be 0 for x less than 0. And this is clearly a distribution function of exponential theta. So, that means your y has exponential theta. So, this proves that among all distributions which are continuous and concentrated on 0 to infinity, exponential distribution is the only distribution which has lack of memory property.